In lecture 4 we've moved a bit further. We've carried on thinking about this vision of gases as being made up of small particles, and we've tried to answer the question why, when, as in the previous lecture, we've worked out that the speed of gas particles is of the order of hundreds of meters a second at atmospheric pressure, why then does it take, for example, 10 minutes for the smell of some perfume to go from one side of the lecture theatre to the other? What's actually going on in real life? Okay, so to look at these things, we've had to consider the actual collisions the molecules make with one another. Okay, and what's important here is we've looked at a quantity called the mean free path, or lambda, which is the distance between collisions. We can see that obviously when the pressure is high and there's lots of molecules around, there's going to be lots of collisions. When the pressure's low, for example at the top of the atmosphere, there's going to be very few collisions. So the mean free path can vary greatly depending on pressure. The other thing the mean free path depends on is the surface area of the molecules, okay, which gives some kind of a collision cross-section. So obviously we're expecting the mean free path to depend on the number density of molecules, how many molecules there are, and the size of the molecules, or in fact the size squared, the diameter squared, which allows us to work out the area. Okay, so we went through a derivation to do this, okay, to find an approximation for the mean free path. And you should all go through this in your lecture notes because it's quite an interesting derivation. And it's an example of where we use physics to try and simplify things and take a simple picture and see how far we can go with that. We've shown at the end of this, really, that the mean free path, typically for a molecule at sea level, is probably 100 nanometers. And that gives us that the molecule is probably having around 10 to the 9 collisions per second. Okay, so from there we went on to ask the question, how long does it take, bearing in mind the fact this molecule's colliding all the time? Can we work out how long it takes for the molecule to go a given distance in a given direction? And to do this we've had to consider what's called a random walk. Okay, so we took the example of a drunk student walking home from the pub, staggering along, bouncing off lampposts, okay, but all the time they're making a small amount of distance towards their flat. The same thing happens with the gas particles, and we worked out a derivation of this based on the cosine rule. And at the end of this derivation we could show that the distance that the particle's making towards the back of the lecture theatre, okay, for instance, depends on the square root of the time. Okay, it also depends on the square root of the mean free path and the RMS velocity that we calculated earlier. Okay, but the key result here is that the particle in the gas diffuses directly proportional to the square root of the time. Okay, so from that we could come up with a value where we work out what was happening with bromine, we could work out the mean free path, okay, we could work out, and from knowing those kinds of things we could work out the velocity, you know, so we've done all of those things using an example molecule. We finished off by just considering briefly the fact that we can now use these ideas of mean free path and density to get a simple approximation for the size of a molecule. What we did, of course, was we looked at the fact that on average in a gas one molecule occupies a volume which is given by pi d squared multiplied by the mean free path, whereas in a liquid where all the molecules are touching, the approximate volume that a molecule occupies is given by d cubed. Okay, we could then divide the densities through and come up with a simple formula to give us the size of a molecule. And what we found with our estimate here is we found the size of a molecule is roughly 0.4 of a nanometer, and that's in pretty good agreement with actual observations when we go out there and look. What we're going to do next time is we're going to go out and think about bigger systems. So I'm going to talk to you about the first law of thermodynamics, and we're going to look at heat capacities and molecular heat capacities. I also gave out a problem sheet in today's lecture. Okay, you should be able to attempt all the questions on that problem sheet, with the exception of question 7 part C, because if you look at the problem sheet there is no question 10, and I apologise for that. I look forward to seeing you on next Monday. Remember, tutorials start next week, workshops start next week, and labs start the week after.